Once we have our input embeddings and our positional encodings, we're now ready to pass this data onto the encoder block, where it goes through a multi-headed attention layer and a feed-forward layer. One of the core components of the encoder block is the multi-head attention layer. It allows the model to weigh the importance of different tokens. This layer gives us attention vectors that capture contextual information between every token in the text. Let's go through the steps to how these attention vectors are calculated. For each token in the input sequence, we create 3 vectors: a query vector, a key vector, and a value vector. For each token in the input sentence, a query vector is calculated. This query vector represents the tokens in question about the other tokens in the sentence. It's kind of like saying, how much should I pay attention to each of the other tokens? To put it simply, you can think of the query vector as the currently attended to token in the input sequence. The key vectors, on the other hand, hold information about all the other tokens in the sequence. Each key vector corresponds to a different token and contains information that helps determine how much attention should be given to that token. Value vectors are associated with each token in the input sequence. Think of them as information containers that hold the actual content or knowledge about each token. When the query token, the token currently being attended to, asks questions about attending to other tokens, the value vectors provide the answers. The values for these different vectors are what's learnt through training our model. The next step in the process is that we calculate the similarity between each query vector and all key vectors using dot products. This produces a set of similarity scores, one for each token in the sentence, indicating how much attention each token should receive from the currently attended to query token. To ensure numerical stability, we scale the similarity scores by dividing them by the square root of the dimensions of the key vectors. This scaling factor helps control the magnitude of the scores. Next, we apply the softmax function to the scaled similarity scores to obtain an attention weight. The softmax function normalizes the scores so they sum up to 1, effectively turning them into probabilities. So, now we have an attention weight for each token in the sequence, indicating how much attention the query token should give to each other token. We then calculate the weighted sum of the value vectors, using the attention weights. This step aggregates information from the entire input sequence, giving more importance to tokens with higher attention weights. The resulting attention vector represents the combined information from the input sequence, focusing on relevant tokens based on the attention mechanism. We say that this layer of the transformer architecture is multi-headed because transformers will try multiple different iterations of query, key, and value projections, known as heads. Each head learns a different set of weights, allowing the model to focus on different aspects or patterns in the data. The attention vectors from each head are concatenated and transformed to produce the final output of this layer.